Hello again, my dear students. Now this is second part for the MOSFET chapter number 3 in the electronic course. In the previous chapter, or sorry, in the previous part, we have studied together what we can call the MOSFET principle, the region of operations, the IV characteristic curves, the equations related to the current and the voltage, the resistance in the triad region, as well as current voltage dependent current source in the saturation region. Now we are going to apply what we have studied into circuits. In this part and in the next part, we are going to do the main two types of analysis for a MOSFET circuits. What we can call the DC MOSFET circuit analysis and the AC MOSFET circuits analysis. It's easy to recognize that in this part, we are dealing with a DC circuit whenever the variation or the circuits in the MOSFET is a DC. And then in the next part, we are going to deal it with an AC analysis. Actually, the general or the generic formula for a MOSFET circuit is to have an AC inputs. However, as a first step, in order to study any AC MOSFET, we have first to make what's called the DC analysis by deactivating all the AC sources. So this, or what we are going to do in this part, is principally the first stage in analyzing any MOSFET circuit. Now let me go back to my presentation slide and start this journey. Okay, so we will start with examples. Of course, whenever it's circuits, it's more logic to do it with examples rather than to illustrate series. So this is our example. We have a circuit looks like that. We have a voltage source, we call it VDD, with a 10 voltage. This is two equally weighted resistance of 10 mega ohm. This is a 6 kilo ohm resistance, another 6 kilo ohm resistance. This is our source, this is our drain, and this is our gate. As you can see, what is required is to calculate the drain voltage, which is this value VD, and the drain current ID. Okay, before going into calculations and before turning to our whiteboard, I have to mention a very important point related to any MOSFET analysis, which is this branch, the gate branch. If we go back to the schematic here, for example, as you can see, there is here an oxide layer. And this oxide layer means that this is an insulator. Accordingly, no current, again, no current is flowing in this branch, because simply you have here an insulator with a very high resistance. So in all our circuits analysis, we will consider the current flowing inside the gate is equal to 0. So in all time, this IG or I gate is equal to 0. This is a very important tip whenever you are doing some calculations. Okay, perfect. Okay, so back to our whiteboard, and this is a circuit we are going to demonstrate in this example. Again, we have two resistance here, 10 mega and 10 mega. This is the gate voltage, this is the source, and this is the drain. 6K resistance, 6K resistance, and I forgot to mention that we have here VDD, which is 10 voltage. This is the supply, and as a given, as I told you, the term can dash W over L will be always given. So this is 1 milliampere per voltage square. So this is the overall circuit schematic we are going to solve. What we are seeking for is to calculate the voltage on the drain and the current flowing from the drain to the source. This is what is requested. So, okay, let's start together. So at the first step, I just told you that we have a very important note that the voltage flow inside the current flow inside the gate is equal to 0. That means that there is no current here, and that means that this is simply a potential divider. You have a voltage, which is 10 volt, which is equally divided between these two 10 mega ohms. So accordingly, the voltage of this point is simply 5 volt, which is, by the way, the gate voltage. So VG is equal to 5 volt. Now you know VG. But if you recognize well the IV characteristic curve for a MOSFET, you know that we have two regions of operation. We have what's called the triad region, and we have what we call the saturation region. And the difference or the reference that I'm in a saturation or in a tribe is the value of the voltage VDS. So we have to compare the value of the voltage VDS with respect to the VGS minus V threshold. So if VDS is greater than VGS minus V threshold, then you are in the saturation mode. If VDS is smaller than VGS minus V threshold, then you are in the tribe mode. But unfortunately, we know nothing about the VDS. We don't know the drain voltage, and we don't know the saturation voltage. Sorry, the source voltage. And even we don't know VGS, we just know VG, which is a V gate, but we don't know VS. This voltage is a VS. We don't know it. It's unknown. And based on the given we have, we don't have anything or any information that can lead to know what is the value of VD or VS. Accordingly, we have to have an assumption. But please take care that this is just an assumption. So what I'm going to do now is the following. I will say, okay, I will assume that this MOSFET is working in the saturation region. It's just an assumption. Then, if this MOSFET is working in the saturation region, I have the equation for the saturation region. I know that in a saturation region, the ID or the drain current is given this. Kn dash W over 2L times VGS times V threshold, all square. By the way, I forgot to mention that V threshold is also a given, which is 1 volt. I'm sorry. Okay, perfect. So you make an assumption. This assumption may be right, may be wrong. We don't know. But this assumption says that the MOSFET is in the saturation. So this is the equation. Kn dash W over L is given. You just need to divide it by 2. So ID is equals to this 1 times 10 power negative 3. It's 10 power negative 3 because we have milliampere here. So don't forget. Over 2. This is 2. Okay, because I think in the problem it's given, yeah, it's given W over L, so we have to divide it by 2 times, yes. We know VG, which is 5 volt, but we have no information about VS, so it's 5 volt minus VS. You just know VG, but you don't know VS. Minus VT, which is the threshold voltage, we know it's 1 over square. Okay, so this is an equation. But still we have two unknowns. Even after we did the assumption, we still have ID is an unknown, we don't know ID, and VS is an unknown, we don't know VS. So let's think about it a bit. So we need another equation. You have one equation with two unknowns. So we need another equation in order to solve this circuit. Let's again so this is the VDD, which is 10 volts, and we have here this is VG, which is 5 volts. Just I get rid of these 10 mega ohms because we don't need it. This is 6K, and this is 6K. This is, let's make it in a different color. So this is VD, this is VS. The current flowing here is ID, and okay, so this is a current and this is ground. Okay, that's perfect. Done. What we are seeking for now is another equation linking the ID with the VS. So let's check this resistance, this 6 kilo ohm resistance. The voltage drop across this 6 kilo ohm resistance is simply VS minus 0, which is equals to the current flowing into the resistance, which is ID, times the resistance value, which is 6 times 10 power 3. So this is the other equation. This is the second equation you can use in terms of VS and ID. So you have now two equations. The first equation is ID is equals to 1 times 10 power negative 3 Kn dash W over L over 2, 5 minus Vs minus 1 all square. And the second equation is Vs is equals to 6 times 10 power 3 times ID. So what you can do simply is that you can remove Vs from here, and then you can add its equivalent, which is ID times 6 times 10 power 3. So accordingly, you will have an equation saying that ID equals 0.5 times 10 power negative 3, which is simply 1 over 2 times 10 power negative 3. We have 5 minus 1, which is 4. So 4 minus, and then I will remove Vs and insert 6 times 10 power 3 times ID whole square. So this is an equation. As you can see, this is a second order equation in ID. So by simply going to your calculator and solving this equation, you will get two answers for ID because this is simply a second order equation. So whenever you do it, okay, so by substituting and getting this second order equation, you can get two values for ID. So the two values will be ID equal 0.89 milliampere and ID equal 0.5 milliampere. So these two values are the output of solving the second order equation. Now, which of these two values are correct? Please remember that for a circuit, we should have one exact value. It doesn't make sense to have two values for a current. So which of these two values is correct? Here we have to return back to the start of our solution, typically to this part, the assumption. We assume that our MOSFET is operating in the saturation region. So the solution will be correct if and only if it satisfies the assumption. So whenever you have a saturation MOSFET, that means that VDS should be greater than or equal VGS minus V threshold. Please don't forget that. You only know V threshold, which is 1 volt, and V gate, which is 5 volt. Now we should calculate the source voltage, the drain voltage, and satisfy this equation. For example, let's start with the case with ID equals to, let's say, for example, 0.89 milliampere, which is the first solution. This one, yeah, 0.89 milliampere. So if ID equals to 0.89 milliampere, so now return back here. Vs is equals to ID times 6 times 10 power 3, which is the 6 kilo ohm. So what we are going to do simply is that, let's pick up my calculator. So it's 0.89 times 6. This will result with 5.34. So Vs is 5.34 voltage. Is this an acceptable Vs? The answer is typically no. Why? Because you have V gate equals to 5 voltage. So if Vs equals to 5.34, that means that VGS is a negative value, which means that your transistor is turned off because VGS should be positive and should be greater than V threshold in order to make this MOSFET operate. So that simply means that this is a wrong solution. The second solution is with ID equals to 0.5 milliampere. So this is the second solution. Let's do it. So for ID equals to 0.5 milliampere, Vs will be equals to 0.5 milliampere times 6k ohm, which is results of a 3 voltage. Now, VGS equals to 5 minus 3, which is 2 voltage. Now, this is an acceptable assumption. However, we still did not validate our assumption, because our assumption is that the MOSFET is working in the saturation region. I mean, VDS should be equal to VGS minus V threshold. So you should calculate VDS and you should check this validity. How shall we calculate VDS? Let's do it. Now, this is your circuit. This is 6K, this is 6K, this is 10 voltage, this is VD, which is still unknown, and this is VS, which is equals to 3 voltage. Now, this VD, you can calculate VD, that's true, because you know ID, which is 0.5 milliampere, and the voltage drop on this resistance, which is 10 minus VD, is equals to the current flowing, which is 0.5 milliampere, times the voltage, sorry, the resistance, which is 6K. So 10 minus VD equals 3. That means that 10 minus VD equals 3. So VD equals 7 voltage. Now, you can validate the assumption. Let's see. Where is the assumption? This is the assumption. VDS is 7 minus 3. So this is a 4 voltage. Is it greater than VGS, which is 2 voltage, minus VT, which is 1? So 4 is greater than 2 minus 1, which is 1. 4 is greater than 1. Then this is a correct assumption. So this is this MOSFET is working in the saturation region. Usually, you ask me here. Now let's turn to the first slide. I think yes, this one. Usually, you ask me here, why you assume that the MOSFET is operating in the saturation? Actually, there is no answer for this question. You can assume that this MOSFET is working in the triad. That's true. And in this case, you will first solve to get the conditions, and you will find that this is a wrong condition. So you will solve it again, assuming that it's a saturation. However, assuming that the MOSFET is working in a saturation have a very important advantage, which is this equation will not be a function in VDS. However, if you assume that your transistor is working in linear region or triad region, the equation, which will be K-W over L, VGS minus V threshold times VDS, will be a function in VDS. Then you will have a new unknown in the equation, which is VD. However, whenever you assume that the MOSFET is in saturation mode, then you have only one unknown in addition to the ID, of course, which is VS, or the source voltage. This is the advantage. That's why usually whenever we did an assumption in the MOSFET circuits, we start with assuming that the MOSFET is in the saturation region, not in the triad region. If the assumption works fine, like this example, that's perfect. If not, then you know then in this case that your transistor is working in the triad region and you have to solve it in the triad region. That's all. Okay. So this is the first example we did together. Let's turn now to another example. Let's return back to the presentation slides. Okay, perfect. I think now you can see my presentation slide. This is okay. This is the example we solved it together. But let me make it in a full screen better. Yes, this is a full screen version. Okay, this is the example we solved it together. Now we have another example. Now we have this two circuit. This is two MOSFETs connected in this way. This is a VDD. This is a resistance, as you can see here. So what we are going now is just we are going to solve this example. The required is to get the value of the current ID2 in terms to the value of the current ID1. So let's see how we are going to solve it. Okay, so this is the circuit we have. We have here two MOSFETs, Q1 and Q2. The first MOSFET has this very interesting connection. I will talk somehow about it. Then we have a resistance, a VDD, and this is the current flowing in the resistance ID1 and ID2. Okay, so before proceeding to this circuit, I just need to focus on this connection. This connection is a connection connecting the drain to the gate. As you can see, this is a short circuit between the drain and to the gate. So let's do it separately in the first place. So here, whenever you have a MOSFET, this is a drain, and this is a source, and this is a gate, of course. And you have a connection like that, connecting the drain to the gate. Then that means that VD is equal to VG, or in other words, that VGS equals to VDS. What is the consequences of having VDS equal to VGS? This simply means that whenever you go to the condition which relates VDS with VGS minus V threshold, of course, as these two quantities are equal, then VGS minus V threshold will be all the time smaller than VDS. That means that your MOSFET is operating in the saturation region all the time. So whenever you see a MOSFET connected in this manner, that's typically mean that you have your MOSFET in a saturation. You don't need to assume that it's in saturation because it's by force, it's in the saturation mode. So this is a very important tip related to this MOSFET. Accordingly, my dear students, we can say that the first MOSFET, which is Q1, has a current equals to ID1 equals to Kn dash W over 2L, and I will put some subscript 1 to indicate that this is related to Q1, because as you remember, Kn dash W over L are device parameters, so it can differ from one transistor to another. So this is the yes times VGS minus V threshold all square. Of course, here VGS and VDS are the same. So this is the first equation. Now, what if I will call this again VGS1 to indicate that this is the VGS for the first transistor, Q1. What if Q2 is also in the saturation mode? What if? Then you will have ID2 equals to Kn dash W over L over 2L for transistor number 2, VGS2 minus VT all square. But please take care. The source of the first transistor is connected to the source of the second transistor, and the gate of the first transistor is connected to the gate of the second transistor. So simply, VGS1 and VGS2 are equal. Accordingly, these two brackets are identical. So you can say that ID1 over ID2 is equals to Kn dash W over L for transistor number 1 over Kn dash W over L for transistor number 2. If these two, because simply you can cancel this bracket with this bracket. So if these two parameters are identical, so you have the same material parameter and the same dimension for these two transistors, then the current flowing in ID1 will be typically equal to the current flowing in the ID2. That's why we call this circuit as the current mirror, because you are just mirroring the current. And additionally, you can add some gaining factor here. For example, if you have one transistor with double the channel length with respect to the second, then this will affect this ratio. So you can also add some amplification of attenuation to the current with respect to this ratio between W over L and W over L and K dash and K dash. So that's why we call, as I mentioned, the current mirror. Okay, so this is two examples we have demonstrated together, representing some examples for the DC analysis from MOSFET. As I mentioned, I name it, or we call it a DC analysis because as far as you see, we are using only DC supplies, which is mainly this VDD source or some voltage inserted to the gate, like in the first example, again in the DC format. What we are going to do in the next part, which is part number 3, that we are going to turn to what's called the AC analysis for a MOSFET. However, as I mentioned, even in the AC analysis of the MOSFET, you will find that you still need to do a DC analysis first. So that's why this DC analysis is an obligatory step whenever you are dealing with a MOSFET. My recommendation, my dear students, is to access the tutorial problem, to access the reference, and start solving more and more circuits with the DC analysis. The larger number of problems you are going to solve, the higher and higher understanding level you will reach. This is very important whenever you are dealing with electronics and circuits. Thank you very much for your concentration, and see you for the next part, inshallah.